I'll be talking about first the history of analyzers, then how semi-automated analyzer came into existence and how they helped the human beings who were doing the manual counting, spending so much energy and time. Then how the semi-automated analyzer, hematology analyzers are being overtaken by a fully automated analyzer, how they change the lives. We will talk about most common different type of analyzers which are present in the market, the basic principle of those analyzers in a simplified form. And if the time permits, we can talk about the interpretation, and I'll show you some examples of the analyzers. So first is history, very much important. And I thank myself. I should thank the God there, and you should also thank God that you were not born in 1950s. Because if you were born, most of your PG must have gone using this Newber's chamber to count WBC, RBC, platelet, and all the manual work. So thank God we all people were not born in 1950s. You'll be surprised to know that 5-part differential came long back we were born. That is 1974 was the time when the first 5-part differential came. And this 5-part differential later got modified into 6-part, including the immature granulocyte, and machines started counting NRBC also. So this is a timeline from 1950s till date. Now the next part was that how manual count was overtaken by semi-automated. So first you should understand that manual count was very time consuming. There was no precision, there was no accuracy. We had to mix the samples manually with the hand. And of course, the storage of the data. We had to do all the manual work. So there were long list of registers and files which were maintaining the data. And 100% of the slides were made. That means all the samples which were received, the slides were prepared. It was later on taken up by semi-automated analyzer, which was time consuming, but the time was reduced. The precision was better, accuracy was much better. Mixing was still with the help of manual thing. We had to mix it with the hand, and storage of data became little better. Of course, the same problem, 100% of the slides were made. Now, why this 100% of slides were made in semi-automated analyzer? The simple reason was that the semi-automated analyzer was only able to differentiate the entire population, the entire leukocyte population into small, medium, and large size. Later on, we had to use this, we had to see the slide for differential, that is, which of those were eosinophil, lymphocytes, neutrophils, monocyte, and abnormal cells. So in this way, semi-automated analyzer in a small place or in a small lab can be helpful, where you have a good support of a pathologist, so that all the slides can be prepared and differential can be done. Still, semi-automated analyzers are used nowadays in smaller labs. So the type of analyzers which came up gradually changed from 3-part to 5-part and then to 7 parts. Now first, the 3-part analyzer. It looks like this commonly, and here you can see a probe. And this probe is a place where you have to put your vacutainer each time and press the button so that aspiration takes place inside the instrument. So this is a typical 3-part differential machine. Now, this 3-part differential was based on one principle, which you have to remember. The word is impedance. Every time we talk about, we have to talk about impedance. Impedance in the literal meaning means hindrance, wherever there is a hindrance. The principle I'll talk about, but let us see the photographs first. The photograph on the right side, you will appreciate, if you have seen this machine, this is Beckman-Coulter LH750. Which was later modified into Beckman-Coulter 900, and you will see this is Beckman-Coulter 800, sorry, and this is Beckman-Coulter 900. So gradually this was the timeline of the Beckman-Coulter machines. I'm showing you another most common machine, that is Sysmex. Now this was a XE series which was later replaced by XN series. So presently in most of the labs in the market, they are using the XN series. Along with these two companies, there are also other companies like Abbott is there, then Edvia machine is there, and then coming up is Horiba, and nowadays Mindray is also coming. So these machines also are used in various labs. So as a PG student, you should be aware of different type of machines which are available currently in the market regarding the hematology analyzers. Now I'm switching to the principle of these machines. What all is happening inside these machines? And it is a very interesting story, like the morphology Dr. Prerna has told you. In the same way, analyzer also has a beautiful story inside what is happening around. But before that, for your viva purpose also and for your knowledge also, you should talk about what is the principle of the machine. So the first thing is impedance measurement, then is optical measurement in the machine, then machine use radio frequency, and then is fluorescent flow cytometry. Now these four principles I'm talking about the machines, different machines, and in different type of company make you have different principles. For example, if I talk about Beckman-Coulter, which is mainly composed using these three principles, that is impedance, optical, and radio frequency. When we talk about Sysmex series, then additional fluorescent flow cytometry also comes into the way. So I have talked about the timeline of the instrument. I have shown you different types of instruments. I have talked now about the principle of the various machines which are used for hematology testing. So we'll start the first principle that is known as the impedance principle. Now first you concentrate on this diagram. This is very important diagram, and you'll be surprised to know the impedance was introduced by scientists Beckman and Coulter. So that is why this is the patent of Beckman-Coulter, that is using the impedance. Although this principle is used by various machines by the different companies. Now, what is this principle? If you can appreciate a simple way, it has been shown that in the jar, if an electrolyte is in the electrolyte, the blood cells are suspended and two electrodes are placed, one inside and one outside, and the current is made to draw. There will be a drawing of the current through this aperture. Now, whenever the cell passes through this aperture, in the presence of the electric current, there is a hindrance in the connection or hindrance in the flow of the electric current. And that hindrance is taken as impedance or hindrance and is reflected in form of a wave, or we can say change in voltage. If the similar cells are passing through this aperture every time, let us say RBCs, the data of these impedance waves will be collected at one place. In the same way, when the neutrophil, which are smaller in size, are passing through this aperture, and let us say multiple neutrophils are passing, they will produce less of a hindrance compared to the RBC. In the same way, when neutrophils are passing, they will produce more hindrance compared to neutrophil and platelets. So let us read this. The impedance method is a cell counting and sizing technique. So what is appreciated here when the impedance takes place? Number of cells passing through that hindrance or creating the hindrance, and what is the size of each cell. So with the principal impedance method, we can find out how many cells are there and what is the size. Mind you, these are the two things which you will be able to understand, or which the data will be generated through impedance is only of the size and the number of cells, nothing else. So the basis of this measurement is that changes in the electrical impedance or resistance is produced whenever the particle, that is the blood cell, passes through the aperture. So this measures the size of WBC, size of RBC and platelet, as well as the number. So as the cell pass through an aperture of the known size, they cause a change in electrical conductance, which is proportional to the size of the particle. So if 1, 2, 3 cells are passing through it, the machine will produce 3 pulses. And if the 3 cells are of similar size, let us say RBC, These pulses will be of same height. So they will combine together to help in formation of a cluster, or we call it as a histogram. So impedance is the basic principle of three-part differential, and in every machine on earth, impedance is used as an initial method to count the number of cells as well as the size of the cell. So ultimately, through impedance, what data is generated? It is the histogram which is generated, which you can appreciate in the coming slides. Now, this is a diagrammatic thing which I wanted to show you. Look at this. The electric current is flowing. There is an aperture. The cell passes through the aperture. There is hindrance in the conduction. And that hindrance is shown in form of or is gathered in form of a pulse. And these pulses together, number of pulses will be number of cells. And the location of these pulses on the graph will be the size of the cell. Now look at this second diagram. You can appreciate when it passes, cell passes in front of, cell passes through this aperture, a wave is generated. Again, another cell passes, another wave is generated. Why different waves? Because the size is different. So ultimately, with the help of the, impedance method, you can appreciate the cells are separated into lymphocyte or the small cell, middle population, and large cell or the granular cell. So this is a basic principle in three-part differential machine. Wherever machine is there, whichever machine is there of whichever company, there is impedance in that, which is separating the neutrophils, or we should say granulocytes, middle population, which consists of eosinophil, monocytes, basophils, and then is the lymphocyte, which is the smaller size population. Now, after talking about impedance, I would like to talk about BCS. Now, BCS technique was an additional technique. What happened? I'll tell you a story. What happened when Beckman Coulter first discovered this impedance method? Sysmex used that impedance method and later on used the fluorescent method also, and then was able to show that we can separate the population with the help of fluorescence as well as impedance into different 5-part components. Those 5 parts was neutrophil, lymphocyte, eosinophil, basophil, monocyte. Okay. Now, Coulter thought that what additional thing I can use along with the impedance so that my machine is also able to differentiate it into different parts. So VCS technology was introduced. The VCS full form is, that is volume, conductivity, and scatter, was utilized by Beckman Coulter to separate the population into 5 generations. So we'll see that. First, we will talk about volume. How volume was measured and how the volume was able to separate the population. So volume is based on the similar electrical impedance method. It is highly accurate for the measurement of, again, I'm talking about cell volume. Different sizes of cell can be appreciated regardless of their orientation. So we can, with the volume method or the electrical impedance method, we can measure the size of the cell. Next came the conductivity. Now, when conductivity was introduced, it was, the principle here used was that whenever the radio frequency waves are made to pass through a cell, those frequency waves will enter the cell membrane, will pass through the cytoplasm, through the nucleus, and will exit. So, since impedance was measuring only the size of the cell from outside, the conductivity radio frequency waves went inside the cell to measure or identify the cell. So radio frequency was able to penetrate, and not only the size of the cell was more specific, but also the internal structure, the chemical composition of the cell was appreciated. And on this basis, the WBC count was differentiated. Next came the scatter. Now, scatter you must have read in your physics classes. And scatter is when the ray of light is made to pass through a cell, the light is scattered. Now, this scattering was taken as forward scatter and side scatter using the 2 multiplier, diode tubes, and those data were generated later on to find out how much the scattering takes place with the neutrophil, by the eosinophil, by the monocyte, and on those basis, the population was divided. Now, Coulter introduced this Bcs scatter system and measured the range of scattering from 10 to 70 degrees. This was helpful to look for granules inside the cytoplasm, how much the nuclear lobes are there. So when you talk about nuclear lobes, you can say there is immature cells in the neutrophil series, or this much of band cells are there, and thus the data could be taken out. So this helped in separation of the different cells. So VCS technique was taken care by the Beckman-Coulter. So you will be surprised to know that while doing a differential, we are looking at only 100 cells in the peripheral blood, but machine is well oriented with the use of algorithms and various softwares. It is able to differentiate 8,192 cells from each sample to differentiate into various type of cell population and divide them according to their volume, conductivity, scatter, or fluorescence into different axes. Now, this is a scatter plot which is generated. We call this as a scatter plot. Those who have the initial starting of this course, you should understand that this scattering you can see here, these are different populations. And this is all pale in color. Pale, or we say it is gray in color. This all is gray population, gray data which is generated from the machine. Now this is not colored, and the color is given by itself. We can give this color, or the machine systems can be given the colors this color. Only we have to see that this is a cluster where the volume of the cluster is less compared to rest of the population, and the scattering is also less. So you can appreciate on the x-axis, this cluster is close to less values. In the same way, this blue cluster is close to lesser values on the y-axis. So what it can be? It can be lymphocyte, because the size of the lymphocyte is less and the cytoplasm itself is also less. So less of scattering is there. So in this way, the color is not from the machine. The color, I mean to say, is given by us. We can change these colors also. In the same way, if you appreciate this population, you look at this population here, the size is very big. That is, size is big because it is showing y-axis, the population is at the higher level. On the other hand, if you look at the x-axis, the scattering is less because it is lying next to the, regarding this, it is lying next to the lymphocyte. So what population it can be? It can be, anybody? Any guess which population is this green color? Anybody can try for this?
Monocyte.
Yes, very good, Charu. This is monocyte. So why monocyte is showing low scatter here? Because it's an agranular cell. The granules are usually absent from the monocyte. Next population, who will guess this? Yes, Astha. Which is this pink population? Anybody else can try? Yes, Charu?
Ma'am, this is neutrophil.
Okay. Yes, this is neutrophil. Very nice. So why neutrophil it is? Because here the volume is similar to that of the monocyte. But as you can see, the scattering has increased. This is because of the granules, which are xerophilic granules, which are present in the neutrophil. Now, what is this orange population? Yes, anybody? What is this orange population you think is? A population which has highest scatter. Yes, anybody? Yes. Yes, it is eosinophil. Why? Because you can appreciate those big granules inside the eosinophil, and those granules are causing more of a scatter. So highest scatter is of eosinophil. So this I have shown you as an example of scatter plots which are generated with the help of various techniques. So the blood is circulated in the body. In the same way, let us see what happens inside the analyzer once the blood is aspirated. Okay. Inside this, if you look at this, sorry. Now, if you look at inside this chamber, you can see the aspirated blood, which has been through the analyzer, you have aspirated around 35 microliter it is. This aspirated blood inside the analyzer is divided into 4 different aliquots. Now, what happens to the first aliquot? The first aliquot is delivered to a chamber, which is mainly for RBC and platelet dilution. So we can say the first chamber where the blood enters, in that chamber, the RBC and platelets can be counted and other additional data could be taken from those things. Now, what happens inside this first chamber? The blood is first diluted with the help of diluent. Now, you can appreciate those big boxes of diluents are lying close to your analyzer. So those are the diluents where those diluents are used. And these diluents, first they dilute this amount of the blood. Now, after dilution, the diluent chamber here is based on the impedance method. You can see here in the first chamber. And the same RBCs and platelets will now pass through the electric current after dilution. And the hindrance which is created here will generate certain pulses. Okay. Now, when the pulses are generated here from RBC and platelets, now see what happens. A histogram is produced. So this histogram, we can see here, it is between the relative number of the cells or the RBC and the size or the volume of the RBCs here. Okay, so that means the most common size of RBC which is generated is this population. That is around 31 femtoliter. And the smallest size, smallest population is at the borders. So what we can do is, with the help of this RBC histogram which is generated now, we can count the number of cells first thing, then we can have mean cell volume. This will be your mean cell volume. Then you can look for red cell distribution width, that is coefficient of variation as well as standard deviation from this histogram. So what 3 things we have derived from it? Can anybody tell me? What are the 3 things from this RBC histogram generated you can get?
Ma'am, mean cell volume, we can see RDW.
Yes.
And predominant RBC size. Yep.
Yeah, the predominant RBC size is your MCV, that is true, and even the count also. So how many pulses are generated through the impedance will give you the RBC count. Now, what is the size of the mean size of these cells, RBCs? That is your mean cell volume. And what is the distribution of the sizes of different RBC? That is known as red cell distribution width. That also we can derive from it. Okay. So we can derive standard deviation, red cell distribution standard deviation from this, and CV we have to calculate. RDW, CV we calculate, that we will talk later. So this is regarding RBC. Now, can you, I'll show you later on. Just imagine in this chamber, the RBC things have come up. In the same way, we have to count the platelets. So whenever there is impedance in the passage of the platelet number are counted and the platelet volume is counted. Generally, what we do, if we scale out, the platelets are counted from 0 to 20 femtoliter and RBC are counted from 20 to 35 femtoliter. That means all the population more than 35 femtoliter is taken as WBC population. The next slide is about RDW and RDWSD. and CV. So can anybody tell me what is the difference between RDW, SD and CV? What does the machine count directly? RDW, SD or CV? Yes. Kanika, any idea?
Ma'am, CV.
No, machine doesn't count CV. The thing is this, machine counts the standard deviation. You can see here the diagram if you can appreciate this. This y-axis, again I am telling you, is the number of cells, and this x-axis is counting the, or is the volume of those cells. So if you consider the peak or the tip of this Gaussian curve and you take it as 100% population, at 20%, if a line is drawn and it intersects at this point and the another point, point 2, and you draw a straight line on the x-axis, then the values which are at 2 and 1, if you subtract it, that will come out to be RDWST, standard deviation. That means 99% of your RBC population is lying between this 1 and 2 region. So this is the area of your histogram, and 99% of your population is between this. So we are talking about red cell distribution, how the size of the cells are distributed. That is why I'm saying RDWST measures the N-isocytosis, not poikilocytosis. It is the variation in size of the RBC which is measured by RDW. Now this standard deviation, when you divide it by the MCV, it will become RDWCV. Okay, so you need to understand that both SD and CV is given in your reports. Do you find this in your reports from hematology analyzer, the printouts?
Yes.
Yes, Charu?
Yes, ma'am.
Both are given, SD and CV?
जी ma'am.
तो क्या देखते हो बेटा, SD देखते हो you see or CV you see?
We see CV.
Yeah, you see CV. So what is the unit of CV? RDW CV? Is it percentage? Yeah. Notice नहीं किया?
जी ma'am.
हाँ. So what is said in the books and the experience of experts is that usually people see CV, RDW CV, but you have to look into SD also, standard deviation. Sometimes what happens, you will find your MCV is normal, and what problem you have is your SD, CV is very much increased, but your MCV is normal. In those situations, which we will discuss in later sections also, the SD is important. At present, I'm just telling you there are two components, SD and CV, and these components have their different importance. So the reference range for CV, RDW CV is from 12.5 or 4 to around 14.2%. Whereas SD, it is around 39 to 47 or 44%. 44, not the percent. So this is the standard deviation of, they have a different importance. Later on, I will tell you. So from this histogram, we have derived MCV, RDW, and the number of RBCs. And the calculated parameter, if somebody asks you, you should know it is hematocrit, MCV, and MCHC from the analyzer. So whenever the derived parameters, that is your number of RBC or your MCV or your RDW is changed, they will directly affect the calculated parameter, that is MCH, MCHC, and hematocrit. Okay. Now we come to platelet count. As I have told you, when you are talking about the impedance, the platelet are counted through impedance method, and their size vary from, so most of the platelets ideally should come within this range, that is 20 femtoliter, and machine has discriminators, that is lower discriminator, upper discriminator and fixed discriminators. जब फिक्स डिस्क्रिमिनेटर की बात करते हैं तो प्लेटलेट में बिकम्स वेरी वेरी इंपॉर्टेंट. फिक्स डिस्क्रिमिनेटर मीन्स वहां पर एक फिक्स डिस्क्रिमिनेटर है और अ सेपरेटर इज देयर which will separate the population of large platelet from the RBC. Okay, so all the population of platelet, let us say large platelet, which crosses that fixed discriminator will falsely be counted in RBC. So if I draw this graph, this histogram is of platelet, the next, according to impedance principle, will be the next graph will be of RBC. Through the cursor, I am helping you to understand that this graph will be of RBC. And this RBC graph will continue till 35 femtoliter, and after 35 femtoliter, it will be lymphocyte. So everything is according to the size here. Okay. So whenever the platelet count is obtained in the impedance method, the histogram is generated, and this histogram is corrected. Like there is a caricature or a skeleton already about the histogram in the machine, and the platelets which are derived from a particular case, they are actually extrapolated on that skeleton, we should say. Okay. So just I want to tell you that in platelet histogram, what information do you get? You get the number of the platelets which are present and what is the size of the platelet. Now this is a classical case of a platelet histogram where the size is around less than 20 femtoliters. Most of the population average is 10. Okay. Now sometimes what happens, this histogram can be flat. It can be like this, a broad base. That means the mean platelet volume in this case will be very high, and there is variation in sizes of different platelets. Sometimes what will happen is this histogram, you can follow my cursor, this histogram will not go smoothly down. What will happen? This histogram will come up and then it will abruptly end with a cut like this, a cut like this. In that situation, what happens? The machine is not able to differentiate. Either it is giant platelet which are going into RBC area, or it are smaller RBCs which are coming into platelet area. Now, the matter of concern here, you should understand why platelets through morphology that time or slide we have to see. Because what happens if some of the RBCs, small RBC, cross this border line and come to platelet, there will be false increase in platelet count. It doesn't help the RBC because they are in millions. Platelets are in lakhs. On the other hand, if the giant platelets are there and they cross this border and come towards the RBC, there will be false decrease in platelets. So you will be giving a false report of thrombocytopenia. That platelets, giant platelets, which have crossed the border and reached the RBC, doesn't pay heat. Those platelets, the RBC is not paying heat because they are in millions. But since the platelets are in lakhs, this will cause thrombocytopenia. So you should look at the histogram pattern of your platelets. Now, like RDW, the platelet also gives mean platelet volume. So mean platelet volume is the average size of the platelets in the histogram, and it is derived from this histogram. Now, this was about the first chamber in which we have talked about the impedance method and how the impedance method is able to differentiate the RBC and the platelet. It is able to count both the population and can comment upon the volume or the size of those cells. Now is the second chamber. The second chamber, if you look at it, the second aliquot goes into the second chamber, and this chamber is mainly for WBC count, that is total WBC count, which you used to do through Newber's chamber in the manual method times. So you will count, the machine will count the WBC and will give an estimation of the hemoglobin. So the interesting fact here is that the WBC count is directly measured again with the help of electrical impedance, because we have to count the number of the cells. And for this purpose, this chamber has a diluent as well as a lytic agent. So in the first chamber, it was only the diluent, mind you. And in the second chamber, an additional reagent is also there. You will see in your, go to the analyzer and see there is a lytic reagent also there. So what happens in second chamber? The WBC count is Number of the WBC is counted with the help of electrical impedance. And the lytic agent, what it does, it breaks the RBC and removes, or we can say it breaks the RBC and brings out the hemoglobin into the diluent solution. So the lytic agent serves to lyse the erythrocyte, converts the released hemoglobin into cyan methemoglobin, and shrinks little bit of the leukocyte membrane, that is WBC membrane. So second chamber mein what it is being done? The hemoglobin is measured and WBC is counted with the help of electrical impedance. So in a machine, in every machine, I should say, all the particles which are larger than 35 femtoliters are counted as leukocyte. So now, students, you understand this, how the impedance is working on the size of the different cells. So 0 to 20 cell size will be taken as platelets. 20 to 35 femtoliter size will be taken as RBC, and all the cells which are more than size of 35 femtoliters will be counted in WBC. The same principle is working to separate the platelet, the RBC, and the WBC. So inside each machine, there are corresponding 3 channels, 3 impedance, you can see 3 impedance channels to count the WBC. That means the cells have to pass through 3 chambers at the same time, and the number of the WBC are counted at the same time. If the mean values matches, each of them, if this value matches, then the WBC count average is taken and is displayed in your, what you call is your, or on your screen, or you're in your printout. तो जो WBC count तुम्हें मिल रहा है machine में, उस WBC count को 3 different chambers, they count them, they take out the average, and if there is a consensus, then only that report is released or that value is given to you. In case there is a discrepancy between 3 of these chambers, suppose this first chamber is giving you 6,700 cells, other is giving 3,400, and another one is giving 6,000, again 700 cells, then there is a discrepancy between the between these. So in that situation, the machine counts again the WBC until and unless they get the answer that it is 6,700, and then the values are released. In case still the discrepancy continues, you are awarded with the star. So you must have seen in your Sysmex machine, with the value, there is a star with it. That means the machine is not sure about the WBC count. So you have to either rerun the sample or you have to approximate with the help of a slide. Yeah, the WBC count is matching with it. Again, hemoglobin method, Beer's law is there, and it depends upon the absorbance. And different machines have different methods. Some use cyan methemoglobin method, like in Beckman Coulter, whereas in your Sysmex machine, it is sodium lauryl sulfate, a reagent which is similar to cyan methemoglobin, but it is less toxic. Next, we come to the interesting third chamber. So first chamber was counting RBC and WBC, RBC and platelet, just for your revision. And there was only diluent in that. The second chamber, where the WBC and hemoglobin is measured, there is a diluent. Along with it, there is a lysate, which is helpful in taking out the hemoglobin out of the red blood cells. Now we come to the third chamber. Now this chamber is important as there is a diluent similar to other 2 chambers, but with a lysing reagent. Now this lysing reagent will remove the erythrocytes and will leave the leukocytes or the WBC in their native state. Okay. So if we talk about Beckman Coulter, this is a chamber in which the conductivity and the scattering of the cells is taken care of. And this is the chamber in your Sysmex machine where the flow cytometry is implemented, or the fluorescent dye is used to identify the different cell population. Basically, the third chamber helps in differentiation of the WBC population, which you have counted in second chamber, into different population like neutrophil, monocytes, lymphocytes. So DLC karne ke liye the third chamber is useful. So this is a scattering I'm showing you. This is more of a Coulter thing. And these are different histograms and the scatter plots which are generated. This is from his Coulter machine. Of course, I think you don't have an experience for this, but These are the scatter plots. Similar to that we see in Sysmex. Colors may be different. Definitely colors are different. And this is a actually 2D plot which is created by Beckman-Coulter, just for your observation. Now this is a scatter plot. 3D plots also we can see in Beckman-Coulter. This is an RBC plot, nucleated red blood cell plot, and these are the RBCs. This is lymphocyte population and list of leukocyte. This is of Coulter. Again, we are seeing the same population under the 2D plot. So next is of story of an RBC. Now the problem is that when you are counting the WBC, the machine has lysed in the second chamber all the RBC with the help of lysing reagent. Now remaining with the WBC are some of the NRBCs if they are present. So that means if the WBC count is counted in those chambers only with the help of impedance, the NRBC will be counted maybe like a lymphocyte, and you will have a false high value of lymphocyte. So it was thought by different manufacturers that how can we separate this NRBC population from WBC when we are doing a peripheral counting. Now these NRBCs, the problem was, I have told you. So this was corrected, or we can say it is being separated, the NRBC population, by Beckman-Coulter with the help of BCS technology. And in Sysmex, they have a different mechanism that I will discuss later and show you the histograms also. Next, we come to the fourth chamber, the last chamber, where I call it a blue chamber. Why it is blue chamber? Because here, this chamber is important because here the reticulocyte count is being done. Some of you must be aware of that. Machines can give the reticulocyte count. It is more accurate, more precise as compared to the human beings counting. And this chamber is present in all the analyzers, 5-part analyzer. It is up to us that we take that staining part, or we take those lysing and staining reagents from the company. Usually it is very costly affair. Somehow the cost of this stain is very high, and most of the hospitals, they don't prefer this method. But if this is a good institute, you can have an automated reticulocyte count. Now what happens in this? The sample is mixed with new methylene blue reagent, and the residual RNA is precipitated within the reticulocyte. This stained sample, which is now stained with the methylene blue, is mixed with the acidic hypotonic solution. What does hypotonic solution do? It elutes the hemoglobin from the erythrocyte and permits the precipitation of RNA. So it will fix the RNA which is present in the RBC, new RBC, and rest of the hemoglobin is eluted out. Another important feature is that inside the chamber, fourth chamber, the RBC, they may be of any shape, let us say spherocyte, or they are elliptocyte, or they are target cell, ultimately changes into sphere. So with the help of this diluting fluid, the spheres are produced by a sphere of the shape of the erythrocyte is of sphere. And once these spheres are produced, either the fluorescent dye is added to it, or with the help of the VCS technology, you can count the reticulocytes. Now, two channels I will like, last slides are these, Wdf channel. Now, this Wdf channel you must have seen in your analyzer, or if you have not seen, go back and see the screen. One of the channel is Wdf. Now, what is this Wdf? It is differential channel. What happens inside this channel? The lyser cell will cause lysis of RBC and platelet. The lyser will penetrate the cell membrane of WBC. This causes little change in the morphology of WBC, and light scatter then helps to differentiate them into different groups. So what is basically WDF is doing? It is helping in creating a differential for you with the help of a lyser reagent, which will penetrate through these WBCs, different WBCs, and hence the shrinkage will be different. For monocyte, it will be different. For neutrophil, it will be different. But all the WBCs, all the neutrophil will have a same shrinkage, and thus will form a cluster. And in this way, a scatter plot is generated. Now, once this penetration takes place, the fluorescent dye, which is added to this chamber, WDF, this fluorescent dye will stain the nucleic acid content in the cytoplasm, that is the RNA, as well as the inside the nucleus DNA, and thus will help to differentiate different population or different type of WBC cells. Moreover, it is also helpful in case of immature granulocyte. So if there is an immature granulocyte population present, let us say myelocyte, metamyelocyte, as we say, shift to the left, then what will happen? The immature granulocytes will have more of DNA and more of RNA because they are rapidly proliferating cells. So they will have a separate population where you can appreciate that there is shift to the left. Next, now this chamber has a limitation. It is not able to separate among these different cell population, the NRBCs. So Sysmex created another chamber, that is WNR chamber. In this WNR chamber, if you can appreciate, this channel will help to differentiate the basophils from the rest of the leukocyte population, as well as NRBCs from the leukocytes. So what it will do? In the same way, the fluorescent stain will stain stronger for WBC compared to NRBC, and hence, because there is less staining of fluorescent dye, the NRBC will be separated from this big population of WBC. Same holds true for the basophils also. The basophils are little resistant to the slicing reagent, and hence the granules remains inside them, the basophilic granules, and thus that population is easily separated from the rest of the WBC. So if I ask you, this population, which is green in color, is basically composed now of lymphocytes, neutrophils, monocyte, eosinophils, minus NRBCs, which are purple in color here, as well as the basophil. Let us talk about these two axes. You can appreciate this is a forward scatter, that is the size of the cell which is determined by it, and SFL. SFL is site fluorescence scatter or light. That is the fluorescence, how much fluorescence are present. So you can appreciate here that leukocytic population has more of fluorescence compared to NRBC. So the WBCs are corrected for the presence of NRBC, but the histograms will not be flagged. That I will tell you later on. So in this way, the machine generates different flags also after the histogram and scatter plot. And these flags are either suspect flag, aap jaake dekhiyega, there are suspect flags, which are software generated flag. And other are defined, well-defined flags, that is definitive flags, which we have put inside the analyzer. So this way I will end up